Yeah, that's right. The ions switch partners. Okay, so a double displacement reaction is when ions switch partners, right? Things completely ionize and they get new partners. And in a precipitation reaction specifically, a solid forms and then separates out from the solution. So this would be, we combine two aqueous things and then a solid is left, right? So that is a big indicator for us that a chemical reaction has taken place, right? If we start with two aqueous solutions and we end up having a solid, that should be a big clue for us that a reaction has taken place. When ionic compounds dissolve in water, the resulting solution contains separated ions. Okay, so ionic compounds, most ionic compounds are soluble. What do I mean when I say soluble? We need to be clear about that vocabulary first. Able to be dissolved in water, right? Soluble is able to be dissolved in water. So when we look at ionic compounds, a lot of ionic compounds are soluble. There are a few that aren't, and the ones that aren't are the ones that form that solid in a precipitation reaction, right? If we join two things, right? If we have four ions floating around and two of them that form are non-soluble or insoluble, that means that they are going to be the solid that is forming, okay? It's not dissolved. It's not soluble anymore, right? It's going to be the solid that forms. All right. Here is an example of a precipitation reaction. We've got barium nitrate and potassium chromate that combine to form potassium nitrate and barium chromate. Looks like I forgot a plus sign there, okay? And then we've got these images down on the bottom, okay? The images are of the particular reactants and then of the product. So let's just look here at the reactants side of our equation. Okay, the reactant side of our equation has barium ions, it has potassium ions, it has nitrate ions, and it has chromate ions, right? When these two substances are dissolved in water, they ionize, right? And then as that ionization is taking place, we see a new formation happening between potassium nitrate and barium chromate. But the reality is that potassium nitrate is also soluble. And so it means really those are still going to exist in their ion state, right? Although we say it is forming a product, in all reality, that's still a soluble compound, which means these are still going to exist just as pure ions. The thing that will exist as an actual compound is barium chromate because it is insoluble, right? It cannot dissolve in water, so it will exist as a solid here. Okay? Yeah, go ahead. I'm going to review just vocab real quick. Soluble means that it is able to dissolve in water. So we use the term AQ or aqueous because that means that our compound is soluble. Okay? If our compound is insoluble, okay, or what the book would call slightly soluble is essentially the same as not, right? Essentially the same as not soluble, insoluble. That means it forms a solid. And so we use S. Okay, so the thing that can get confusing is that when we see an S, we start to think it's soluble. No. S stands for solid. So that means that it's insoluble. Okay, so they kind of can become kind of this overlap thing that can be a little bit confusing. But soluble, we're going to designate with an AQ. And then insoluble, we'll designate with an S because it means that it is going to remain a solid. All right, so here is our rules for solubility. All right, these are rules, again, that you're going to get to use a lot. And these are ones I printed for you on that bigger sheet so that you have them available to you in a little bit bigger form. So the first one says most nitrate salts are soluble. So a salt is any compound that's bonded with a group 1 or group 2 metal. So nitrate with really any group 1 or group 2 is going to be considered soluble. Okay, most alkali metals, salts are soluble, and things that are bonded with ammonium are soluble. So that means almost anything that's bonded with group 1 is going to be considered soluble. Okay, so when we start to build and balance reactions, we're going to now have to reference this page, this chart, to figure out what state of matter are they in. Are they aqueous or are they solid? Right, that's why we're going to start using these. Most chlorine, bromine, and iodine salts are soluble. And then here's where we come in with some exceptions. So that means if we had a compound that was AgCl, right? Although it's a Cl and it says it's soluble, it falls into the exception. So this one would be a solid, right? That would not be an aqueous solution. It would be solid. Okay, so do we see kind of how we read that chart? All we're going to do is come find our compounds on this chart and figure out, are they soluble or are they not? Okay? So it says most hydroxides are only slightly soluble, and it says sodium hydroxide and potassium hydroxide are, but the other are marginally soluble, okay? That's the same as slightly soluble, which is the same as insoluble, okay? So you see these varying degrees. It's tricky to figure out where the line really is, right? But those are all no. And then sulfides, carbonates, chromates, phosphates are slightly soluble, so that means no good, okay? Except for those containing cations in Rule 2. So that means if we have lithium carbonate, we would say, yes, that's soluble because it's in Group 1A. Okay, so we're going to have to use this kind of help us as a guide to figure out what's soluble and what is not. Okay, so let's just try some of these to get an example or to get an idea here. Which of the following ions form compounds with lead plus 2 that are soluble in water? So let's figure out if we had a compound PBS, is it going to be solid? Is it going to be solid or is it going to be aqueous? What? Oh, PBS. It's funny. What do we think? It's going to be solid. So that's no good. What about PbCl2? If chloride forms a compound with lead, what do we think? So it's not aqueous. This one's going to be solid as well. I don't have the rules in front of me, so I'm trusting you. Okay. What about PbNO3 2? I think it's soluble as well because that's rule 1. Most nitrates are soluble. Okay, what about PbSO4? What's it say about sulfates? I don't remember.
It says they're soluble except for Pb and SO4.
Okay, so it's a no. Okay, it's right in our exceptions. Okay, and then what about would Na and Pb form a compound? No, because they're both positive, so that's a no. So the only answer there is C, right? Only thing that's generally soluble would be C. Why is it important for us to know what ionizes, what's solid? Why is it important for us to know that, okay? And it's because when we write our chemical equations, we have to know what's actually happening, right? Before, we've kind of assumed that everything's just going to stay a compound, but now we're kind of figuring out that's not really true, right? If they're soluble, they're going to remain as ions. And then we're going to start looking at electron transfer to see what's changing charges during the reaction, where are the electrons moving during reaction. That's kind of where we're headed here. Okay, so we've got to start to figure out how do we write the basis of our chemical equations. Everything we've done so far has been called the formula equation, right? Writing chemical equations, building and balancing chemical equations so far we've been doing what's called the formula equation, and that's like the basis, okay? So this is an example of a formula equation. It's got all the compounds and it's got their states of matter written in with them, okay? But the compounds are still full. All right. We use our solubility rules to help us determine what is going to be aqueous and what's going to be solid. But the formula equation is the thing we're used to doing. The next thing is called the complete ionic equation. The complete ionic equation. And it says all substances that ionize are represented with their charge and their subscript as a coefficient if there's more than one. So I want to go ahead and write this out. Did I remove this from your slides, or is it on there? It's on there. Okay, I want to kind of show you where that's coming from. So I'm going to go ahead and rewrite it, but I want us to kind of see what's happening here. I want you to first look at our formula equation.
I don't know what you guys are saying.
The thing she erased is gone. It's not there.
Oh, she just erased it up there. It's not on here.
It's not on your slides. That's what I'm saying.
I'm sorry, I thought you were talking about...
No. How about on your slides? Is it there or not there? So you're going to write it out with me. Okay, so let's go ahead and write it out. Together. All right, let's write it out together. Okay, so the complete ionic equation, I want us to write this out. The formula equation, I'm going to go ahead and rewrite the formula equation as well on this slide so we can kind of see it again. The first compound was silver nitrate, AgNO3. The second was sodium chloride. It forms silver chloride and it forms NaNO3. So before we even go farther, I want to go through and check which of those are aqueous and which of those are solids. Okay, I know it was written on the previous one, but I want us to go ahead and dive into that and identify which ones are aqueous and which ones are solid. So looking at silver nitrate, what do we think? Is it aqueous or is it solid? It's aqueous. Okay, so we're going to say aqueous. What about sodium chloride? What do we know about salt?
Oh, yes.
What do we know about salt? It's aqueous, right? It can dissolve. And it fits in with the rule for those chlorides, okay? What about AgCl? Where's your rules for solubility? Right, Ag is the exception on that one, okay? And then all nitrates are soluble, so it's going to be an AQ as well. So there's our formula equation. All I did is rewrite those with us kind of identifying the solid and the aqueous again.
Wait, so what? It says it's not soluble,
But with what thing? When it's bonded with what?
it just says most salts are soluble except AgPb2.
Right, and so this one is bonded with chloride. Is there a rule for chloride? Look at your rule for Cl. Except for? Yeah, so that's what makes it a solid right here. This silver is bonded with nitrate, right? And it says all nitrates are soluble with no exceptions. So Ag is the exception to bonding with a couple anions.
So on rule 3, it says when the exceptions are when they're bonded with Cl, Br, and I.
That's right.
So that's only for CLBR.
Oh, I thought it meant like all of these types of salts are soluble.
The complete ionic equation, you're going to need a little bit of room here. Complete ionic equation is we're going to write out everything as ions. Anything that does ionize is going to be written as its ion. We want to show what's actually happening in the beaker here, what's actually happening in the water. So we said these are aqueous, and if they're aqueous, that means they are going to form individual ions, right? They're going to dissolve in water. And so that means we would be left with Ag, which has a charge of plus, and it's aqueous, plus nitrate, which has a charge of -1, and it's aqueous, right? That is us showing our ionized first compound. Our second reactant is sodium chloride, and we said it is aqueous, and so it will ionize as well. So that becomes Na+, which is aqueous, and Cl-, which is aqueous. Okay, so before when we could just leave off those states of matter, now we have to be more careful and include those. Okay, I'm going to write our products down here on the next line because I don't have enough room. Okay, our products are going to be down here in red. We said AgCl is a solid, so will it ionize? No, and so it gets to just stay. AgCl, we said it was a solid, right? Our last product is sodium nitrate, which we decided was aqueous, so it will ionize, which is Na+, aqueous, and NO3- aqueous. Okay? All right, so that is what's called the complete ionic equation. It shows everything as a complete ion. We wrote the formula equation, the complete ionic equation, and now we're going to write the net ionic equation. So what's net mean? What does net mean? The total, the overall, right? The plus, minus, right? Or whatever you want to say, right? I don't know how you want to say net, but net means the overall. And so in the net ionic equation, we only include components that are undergoing a change. We only include components that undergo a change. So if I look back at my complete ionic equation here, which I'm not sure if I'm going to be able to or not. I might have gone too far. Okay, if I go back to my complete ionic equation, which you could, but I can't. We had all of those ions that were listed there. Did sodium ever undergo a change? Or did it go from a sodium ion back to a sodium ion? It didn't change, right? It stayed as an ion on both sides. What else stayed as an ion on both sides? Nitrate. Sodium and nitrate both had ions on both sides. And so those are what's called spectator ions. Why do you think they're called spectator ions? They don't do anything. They're just watching it happen, right? They're just sitting back, relaxing. They don't have to do anything. So those are called spectator ions. What goes in the net ionic equation are the things that include a change, which would be silver. The silver ion started out as silver aqueous. The chloride ion started out as chloride aqueous. And they form a new compound, which is AgCl. That's a solid. Right? That is now our net ionic equation. This equation, if we do it right, should automatically come out balanced. Right? If we do it correctly, it should automatically come out balanced. Now, all of our ions here were 1-to-1. Right? They all had 1 charges. So it made it really simple. But we're going to do some that don't necessarily have 1 charges, and we're going to have to do a little extra with that, turning that subscript into a coefficient. Right? Because if I have 2 of those and they ionize, now I've got 2 of those individual ions. Okay, so let's look at that here in a second. But do we understand how we write the net ionic equation? It comes pretty simple. Okay, so I'm going to stop there for today.